Okay, we're going to go ahead and get rolling. So Matt mentioned this in his presentation, and we're really excited to have Paul here, who's a program manager at DARPA MTO, to talk about DARPA's latest and greatest grand challenge. With that, I'll hand it off to Paul.
Am I hot? Can you guys hear me? Not too loud, not too quiet. Perfect. So good afternoon, everybody. I'd like to make a passionate plea before I start. Please get your cup of coffee. The post-lunch siesta is really going to bring the atmosphere down in here. So I'd like everyone awake if you could. As Ben said, my name is Paul Tilghman. I'm a program manager at DARPA. I'm here to talk about apparently the third challenge that we're talking about today. I do promise that it has absolutely the biggest prizes of any of the other challenges that are going on. No offense, everybody. It's also a significantly harder problem to tackle. So what I'm going to do here over the next half hour, I'm going to try, I promise, I want to give a brief introduction to sort of the motivation of why we're doing this challenge. And then I want to get into a little bit of the nitty-gritty of what we think it actually takes to do this challenge. And then hopefully conclude by persuading you all to come actually apply your substantial skills against this problem. So let me start with a haiku-esque introduction of the challenge. In really simple terms, it's an open competition. Open competition means everybody here. So it's an open competition where we'll be developing radio networks, full radio networks, that are able to thrive in the spectrum without the need for pre-made allocations. And in order to do that, they're going to have to learn how to adapt across multiple degrees of freedom. And the punchline here, the ultimate goal, is that we want to collaboratively optimize the total spectrum capacity of an ensemble of heterogeneous radios moment to moment. All right, so that's what the challenge is all about in a nutshell, in an attempt to boil it down to 5 lines there. So now let me dig into a little more detail. So I want to start with why we're actually doing this in the first place, and then we'll actually figure out how we got here. The thing that is ubiquitously true, if you are a user of spectrum, your demand for the spectrum is going up and up and up. So these are the commercial Cisco figures. We've been growing in the commercial world basically 50%, a little over 50%, year over year for the last 5 or 6 years running. So if that trend continues, we'll be at a zettabyte of data a month in the 2030 timeframe. So that's a scary amount of demand placed on the spectrum. But this is happening against the backdrop of a finite amount of spectrum, right? We can't manufacture any more of it. We have what we have. And what's more is it seems like it's happening against a dwindling supply. And it's really hard to capture whether our supply of the spectrum is or is not dwindling, but a really good indicator is to actually look at the price of spectrum at auction over the last 10 years. There's been basically a 30x cost growth in how much spectrum is costing at auction. So we have a surge of demand, a finite supply, and a finite supply that at least we feel like is running out. What I'm going to pose to you is that I actually think that this is a byproduct of the way that we manage spectrum. And that's really at the heart of what we're after here in this challenge. So you always need a good story, right? How did we get here? We have exponential demand, seemingly dwindling supply. What actually got us here in the first place? So I want to take you back to 1899. And this is when America really started its love affair with the spectrum. So Marconi broadcast the moment-to-moment ongoings of the America's Cup race across the Atlantic using wireless telegraphy. That was the first time that we as a public were able to watch an event unfold live that was happening far away from us, right? We actually knew who was in the lead before they got across the ocean, right? So this was so impressive that I think a month later, the Navy invites Marconi out and says, come, we want you to install your equipment on a couple of our ships and in shore stations, conduct an exercise with us. that was a disaster. There was a tremendous amount of interference, and it was really due to the fact that wireless telegraphy, spark gap radio, was inherently wideband. So you had uncoordinated ships and shores trying to send messages at the same time. A lot of interference ensued. Marconi refused to actually offer a solution to that at the time because he was trying to protect what many of us now know as the famous 4.7s patent. So in 1900, that was the first time we actually started using frequency on transmit and receive as a way to select and isolate radio systems from one another, preventing interference so that we could have more than one radio system in the spectrum. All right? This is the beginning of what is now boiling to a head in terms of demand versus supply. So take that idea, apply it over and over and over and over again for 100+ years on end, and this is our world today. A chart that, how many of you actually have hanging in your cubes? Now, I guarantee you it's more than that. So this really sort of created a patchwork of isolation, right? We managed the spectrum by doling out bands to specific users or systems or radio types. And it's through this pre-planned patchwork that I would actually claim we've created our problem of dwindling supply, the fact that we don't think there's enough, because we've divided it up ahead of time. And when you rely on pre-planning, you can't respond to the dynamics of supply and demand, so to speak. So this has a number of net effects, but overall it makes us inefficient in the way we use the spectrum. I think this is what's causing scarcity. And very specific, if you think about it from a military context, you're vulnerable. It's very clear where every radio system is going to operate. If you encounter interference where you're supposed to operate, you have very little recourse because that is the area where you're supposed to operate. You can't go somewhere else. So we call today the era of isolation. And it doesn't really matter how you slice and dice it. The way we use the spectrum today is fundamentally about trying to mitigate interference by finding a way to create isolation. Finding a way to make radio systems capable of operating in the spectrum relatively ignorant of what all the other radio systems are doing in the spectrum. So that could be static isolation, dividing the spectrum up into pieces, time, frequency, geography, and having exclusive access to those bands and those geographies. It could be more advanced like we have in the unlicensed bands. I would still submit that that is a form of isolation. The radios don't know very much about each other. All they have is a very simple rule set of I see energy, I need to get out of the way of that energy. And so we're sort of ducking and weaving in the unlicensed bands. And even the more recent advent of DSA in the 3.5 gigahertz band, as an example, is still creating isolation. We're doing it a little more nimbly, but we're not responding to the supply and demand of the spectrum in a time frame of milliseconds and seconds. We're responding in terms of minutes and on very coarse 5 megahertz boundaries. All right, so today is the era of isolation. But what we want to create with the Spectrum Collaboration Challenge is a new era, an era of collaboration. So rather than having no idea what the other systems are in the spectrum, what their needs are, what their interference condition is right now, what kind of quality of service they have, we actually want to foster direct collaboration between a diverse group of radio users in order to come up with, dynamically, efficient strategies at using the spectrum. And we think doing this is really this confluence of software-defined radio, artificial intelligence, aided by collaboration. Ignore all the prizes, we'll get to that. So building these, we call them collaborative intelligent radio networks. There are 5 key components that you really need to a collaborative intelligent radio network. And it starts with the radio itself. If you don't have a radio that is substantially reconfigurable, if you don't have a radio that has knobs, if you can't change your waveform or your MAC scheme or your network routing protocol or your spatial selectivity, if you can't change something about your radio, in response to the environment you find yourself in response to the second-to-second changes. It doesn't matter how smart you make the radio. If it's going to sit there like a bump on the log, it can be very smart, but it's ultimately not going to make the world better. So reconfigurable radio with a substantial number of degrees of freedom is sort of at the core of this problem. That's our base. We need to build on that base. Then what we're going to do is we're going to actually add 4 different intelligent radio characteristics. The ability to understand the RF environment, look out around you, know what's going on. Using our understanding of the RF environment to reason about what we should do, right? Should I point my transmission in a different direction? Should I adaptively create a null? Should I stop using a carrier sensing medium access scheme and go to a time division medium access scheme? So we need to reason based on our understanding. But what's really important here is because we're talking about collaborative spectrum use, it's not just about reasoning about what the best choice is for you or your radio system. You actually need to think about, or your radios need to think about, what is the best choice for the entire ensemble of radios using the same spectrum and the same geography. So we have to understand the environment. We're going to then reason about how to do that, but we're going to do it in a collaborative way. We need to be able to contextualize what we know. If your radio learns how to operate in a particular environment, and then the conditions change, and you have to unlearn and relearn, you're ultimately going to react too slowly to be an effective radio at the end of the day. So you have to be able to contextualize what you know, take your understanding of existing conditions, and figure out how that applies to the situation you find yourself in now to adapt quickly. And last but not least, you need to collaborate. Without collaboration, the best we can do is isolation. If we don't actually directly know how our choices impact other users of the spectrum, the best we can do is guess or make really coarse assumptions ahead of time, which ultimately lead us to where we are right now. Inefficient overall use of the spectrum. So 5 key elements required to build the collaborative intelligent radio. It all fundamentally starts with the reconfigurable radio itself. If you're thinking of entering a team in the competition, we'll talk about how to do that. You should probably be asking, well, what do I actually have to do? You have to build a complete radio stack, PHY, MAC, NET, that is controlled by AI and learning algorithms that are able to adapt to the environments that they find themselves in. You're going to instantiate that in software and firmware using what we call the standard radio node. So all teams in the competition are going to have access to the exact same set of radios, the exact same set of computing hardware, so that everyone is on a level playing field in terms of what your radios are actually capable of doing. The winning design then is, in some sense, the best sharer, right? Who is able to share the spectrum the best with any other network, so paired with any other kind of technology we can find, in any environment, and most particularly, the very hard aspect of this, without prior knowledge. So you don't actually know the characteristics of the other radios you have to share the spectrum with. You're going to find that out on the fly and have to actually learn to adapt in the moment. All right, so you got to build a complete radio stack. It's controlled by AI. You're going to do it in software and firmware, and you're going to do it using the standard radio node that we provide. I want to spend a brief second and actually talk about the fact that this is a grand challenge. So show of hands, who knows why DARPA does grand challenges? What makes them grand? No one? Bueller? Step one is we put substantial prizes out there, but we put substantial prizes out there because these are hard problems. Grand challenges, what's really intriguing about grand challenges is that they're not about the end state of the technology at the end of the challenge. Absolutely not. Grand challenges are about demonstrating that there is a new paradigm that is possible, and about catalyzing the community to come together towards a common goal of demonstrating that new paradigm. And then ultimately, when the challenge is done, that technology needs to go on and be further matured with further research. But the challenge is about showing the art of the possible. So I put a couple examples here of challenges that you may be familiar with. Probably the one that is sort of the best example, because we're also the furthest removed from it in time, is the autonomous vehicle challenges of the early and mid-2000s. Right? That wasn't about, when those challenges were done in 2007, we didn't go, perfect, we've got it. The autonomous car now exists, everyone run out to your local dealer and buy your autonomous car. No, it was about showing that we could create that kind of autonomy. We then needed another, probably 20 years of research to the point where it looks like maybe in the next 5 or 10 years, truly autonomous cars may be a commercial viability, right? So it was about showcasing that this new paradigm existed, but then it was still going to require further research and further development before it actually becomes a part of our lives. So grand challenges catalyze a community towards a common goal. In this case, this is the community we're catalyzing. Lots of people in this room have done lots of different work related to dynamic spectrum access and cognitive radio and that entire cadre of research. Yet, it doesn't really exist in the mainstream. We're at a really interesting tipping point because we are actually truly at the point now where it looks like there is not enough supply to meet the demand, where we would actually consider new spectrum access strategies in order to sort of ameliorate that problem. So this is sort of the call to action to everyone in this room. This is your grand challenge. This is your attempt, your opportunity to catalyze all the great minds in this room towards a single common goal. So, how are we going to do that? Let's talk about the program structure a little bit. So the program has 2 tracks, what we call the proposal track and the open track. The bad news is, if you're hearing this for the first time and you're saying, what's the proposal track? It doesn't matter, it closed a few weeks ago. The good news is that the open track is still open and will be open for another 2 months. And then we'll actually reopen with each phase of the competition. So the difference between the proposal track and open track really just has to do with where you start. The proposal track people submitted proposals to DARPA September 2nd. We're currently reviewing them. But they're vying for basically initial seed money from DARPA. All right? Once they have that initial seed money, that's how they're going to participate in the first phase. The open track teams obviously don't get that initial seed money, but you don't have to write a proposal. The open track teams simply have to go to our website, sign up. Now you're in the open track. Once we get to our annual competitions, everyone is the same. So it doesn't matter if you came from the proposal track or you came from the open track. Everybody is treated the same. The program's broken up into 3 one-year phases. At the end of every phase, we do a tournament-style competition. And we'll talk about actually how those tournaments look here in a moment. So it doesn't matter where you came from, proposal track, open track, everyone is vying for the same money at each of the preliminary events. So there are $750,000 prizes on the line at each preliminary event. And then the final event has $2 million, $1 million, and $750,000 prizes for first through third place. See, I promised we have the biggest prizes of all the challenges here today. All right, so what's a match? I'm going to try and do this quickly, and I have to stare at the screen in order to do it. So when we look at the final competition, what we really want to see, we want to be able to take 5 teams. Each team, remember, is built a radio network, right? Your radio network at the finale of the competition has to be at least a size of 20 radio nodes. So 5 teams, 20 radio nodes apiece, all enter an arena that we call the Coliseum all at once. Their goal is to successfully deliver IP traffic within their network. But their overall goal isn't just for them to successfully deliver their own traffic. They want to find a way to deliver their traffic so that the entire ensemble, so that all teams are able to successfully deliver their data. They're going to do this by collaborating. And the way that we enable collaboration is by taking one radio node in each team. We call that the gateway node, and it's special because it has both an air interface and a wired interface. That is the way that allows each team to share information. So the red team, for example, can share information with the purple team because they each have a gateway node that's connected through something that looks like the internet. And over that, they can pass information and share quality of service, share what they know about the current RF environment, maybe share their future plans. But that's not all. They're not the only people in this environment. We also have what we call non-collaborative radios. Those could be incumbents, legacy systems not capable of collaborating or adapting. They require protection. So we have to afford them protection. They could also look like jammers, whether they're intentional jammers or maybe well-meaning but poorly constructed radios. The group has to be able to operate in an environment where they are not the only users of the spectrum. You may also have these non-collaborative users. So 5 networks, 20 nodes apiece, enter an arena that is complex. Their goal is to optimize the total amount of data that is successfully delivered by all radio networks, the entire ensemble. So to do this, one of the key things is what we call the Coliseum. We need a way to emulate a large-scale environment, and I'm going to push on here for the sake of time, but here's what you need to know. It has 2 basic components. A giant wireless channel emulator, 256 by 256, antennas at 100 megahertz apiece. So that enables us to create a large number of environments, dynamic environments, with all the complexity and dynamics of the real RF world. The other half of Coliseum is 128 of these standard radio nodes, which I'll get to here in a moment. Really quick, just to explain sort of how impressive Coliseum is as a feat when it will be done. Forget actually emulating channels for a minute. Just pretend you wanted to push data around, right? You wanted to be able to take any input and put it to any output, any of the 256 inputs to the 256 outputs in Coliseum. That's 50 terabytes a second of data just to move it around, let alone all the operations that we need to do on top of this. So this is going to take serious RF hardware, serious digital hardware paired with RF front ends that we already all know and love. Let's move on for the sake of time here. So the standard radio node itself, this is what every team will be given access to. It consists of a large rack server and an X310 SDR. The teams then, right, you have software and firmware. Those are your tools. That's how you get to actually instantiate your great ideas. The teams are given access to the FPGA and the X310, to the large multi-core GPP, and we're also going to equip each of the machines with a Tesla series graphics card. So you have a pretty large heterogeneous processing environment with which to implement your algorithms on each of the radio nodes. I thought I'd point out here why this is so, all the work that has been done by many of the people in this room and folks outside of this room as well. We couldn't actually have this challenge without you guys. The challenge is really built on the backs of the good work that has gone into this community for years, right? If we didn't have quality, commercially available software-defined radios, we may have the best ideas about how to build a cognitive radio, but we can't actually make them come to life. And this challenge is about not just theoretically what are good ideas, but demonstrably what are good ideas. And we also have a readily available, what I like to think of as a bucket of parts. The 5 things that the collaborative intelligent radio needs, 4 of them are about making the radio intelligent and how you make decisions. Only 1 of them is about the radio itself. The readily available bucket of parts makes it easy to focus our energy in the challenge on what we really want to tackle, which is collaborative and intelligent decision making, and allow us to sort of not spend too much effort focusing on the basic components of how one builds a software-defined radio. So this community has really gotten us to the point where we can have a challenge like this. Let me close by talking about how to get involved, right? So we want everyone here involved. As I said, the proposal track is done, but the open track is open. The open track will be open through November 1st. Is it on this? November 1st. So you have from now until November 1st to register your team for the open track. The open track is really interesting. You don't have to write a proposal, just have to sign up on our website. But we're expecting a pretty large response, potentially, of teams in the open track. Coliseum, at the end of the day, only has so many actual radio resources to it. So we're going to have to pare down from potentially a large set of entrants to a smaller set of entrants. That's what our entrance hurdles are for. The initial version of the entrance hurdles is actually up and posted on our website right now. So the open track teams will complete past the entrance hurdles. That will help us neck down to nominally 25 to 30 open track teams to participate in the first phase of the challenge. An interesting side note of being the open track is that everyone gets to keep all their IP. And you have substantial opportunities to win prizes. $750,000 prizes at each of the 2 preliminary events, and then the $2 million, and $750,000 prizes at the final event. So there's a lot of money to be won, even as an open track team. So get involved. Go to our website, spectrumcollaborationchallenge.com. November 1st is the sign-up date, and then the hurdle completion is shortly following after that in the mid-November timeframe. The other thing I'll point out about the open track, let's say you're not going to enter a team this phase, but you see all the really cool stuff we do in the next phase. We will be opening the competition every year to new participants. So if you've got a really good idea, but don't get involved in the first phase, there's still an opportunity to join at the beginning of phase 2 and the beginning of phase 3 as well. Building teams is critical. I like to think of this as a multidisciplinary problem in terms of how you solve it. If you're interested in how you form a team or how you actually pull members together in order to form a team, we have a teaming website. It's on our website. If you want access to that, email us, sc2@darpa.mil, and we'll get you set up with an account on there so that you can find other folks that are also looking to build teams. And in a very cheesy fashion, seriously, we want everyone here to be involved. This is probably the one and only DARPA Grand Challenge that is really going to speak to this community. Please get involved. Go to our website, sign up. We want to see you guys. Use your years of good work and your expertise and knowledge to show us what it takes to beat this challenge. I think with that, I have how many minutes for questions?
Yeah. So questions from the audience. And actually, in the meantime, if Matt LePan could come up and start getting set up.
For phase 2 and phase 3, will there be further entrance hurdles?
The entrance hurdles will be evolved. So think about this. If you join in the second phase of the competition, everyone that has done a really good job and won those top prizes in the first phase is already substantially far along. So you've not only got to prove you have what it takes, but also that you're at least close to the same level as the folks that completed the first phase. So the hurdles will get tougher as we go throughout the competition to try and incentivize you to get involved earlier.
Other questions from the audience?
Can you quickly iterate what it takes for non-US citizens to participate?
Yeah, so we actually went to some great lengths to make sure that this was not a US-only competition. The specific details are in the eligibility section of our rules document on our website, but the short answer is that this is open internationally. More or less boils down to as long as you're not on an embargoed country trade list, you can participate in this challenge. It's the US military after all, folks.
Go ahead.
Will scaled down versions of the
Disembodied voice, where are you coming from? Thank you.
will scaled down versions of the Coliseum simulator be available for teams to practice before the competition?
An excellent question. I think I'm going to have to punt on that for now. What I can tell you is that I'm definitely not buying small versions for teams to go use. And there's actually a good rationale behind that. I don't know if I mentioned it when I briefly went through Coliseum, but Coliseum's a remote resource. So just because you can't physically touch it, we want all the teams to remotely have access to this very large resource. Because you may be able to easily have a couple of X310s in your lab, but to have a large number of them there's a cost barrier there. And what's more, to actually be able to emulate the RF environment with some amount of realism is also a pretty substantial cost hurdle.
Okay, then a follow-up question then I guess I'm assuming that it'd be available for, say, practicing for teams that have already entered.
Absolutely. So if you're an open track team, once you complete the entrance hurdles, you have Coliseum as a resource that you can use to practice, and we'll also be offering or structuring scrimmages throughout the program. So it's not just your opportunity to practice and use the resource by yourself, but also to give some opportunities to practice, I want to say against, but really with the other competitors that are in the challenge.
All right, we have one over here. In the meantime, Paul, would you mind if he connects his laptop up?
Please.
So a question on the collaboration part.
Yes.
So I can see how you could measure how well your own network performs. How do you measure how collaborative you're being with others?
How does who measure?
Well, so I think you mentioned like one of the ways a team is judged is how collaborative they are with the other networks. So how would that be measured?
So the exact scoring formula is still an item that will be worked on for a bit of time here. But the basic principle is this. If you've done a good job communicating in the spectrum, then you've created opportunities for the other teams to also be able to communicate in the spectrum. And so the score is basically a part combination of how much data you move and how much data is successfully moved by the other teams. So a team score you could think about as having two parts. One is the data you move, and then the other part is the data that's moved by your peers. And those will be composited through some function. That's how you'll ultimately achieve your score for any one match.
All right, I'm afraid that's all the time we have, but please thank Paul